All right, we're gonna make another video because the people, I've heard they want more of this. So we're continuing in chapter 7, section 3, uh, picking up with another example. This is an example of creating a confidence interval for a proportion or a percent. So in example 7-9, it's talking about covering college costs. I'm just going to do this. So it says a survey conducted by Sally Mae and Gallup of 1,404 respondents found that 323 students paid for their education by student loans. Find the 90% confidence interval of the true proportion of students who paid for their education by student loans. Okay, so let's first of all go ahead and figure out what we have to do. So here it says there were 1,404 respondents. So our sample size N is 1,404. I believe, if memory serves me correctly, it said that 323 of the students paid for or financed their education via student loans. It said we want the 90% confidence interval. So that means alpha is 0.1 or 0.10. Okay. So what does that mean? Alpha over 2 is equal to 0.05. Okay. So that means we're looking for the z value. That leaves us with a left area of 5%, and also the corresponding opposite positive z value that gives us a right area of 5%. So that'll make up the missing 10% and leave us 90% of the time having that true proportion within our confidence interval, right? So let's go ahead and do that now. Let's pause so we can both go ahead and look up the z value. Make sure to hit pause, not stop. Okay, we'll jump back in right here. And as we can see, we're at negative 1.6. Looks like we're in between, halfway in between the 0.04 and 0.05. That's where exactly 0.0500 would be. Look like it would be right around there. And at any rate, since we're going to split the difference, we're going to round it up. So that is going to be our critical z values, z subscript alpha over 2, or if you want, you could write in 0.05 in place of alpha over 2. That would be plus or minus 1.65. So again, instead of saying it's 1.645, we'll just go ahead and round that up to 1.65. All right, so there's our critical z value. All right, oh, I'm getting ahead of myself. Before we do anything, we need to know p hat. So that is going to be defined as x divided by n, the number of successes, divided by the total number of participants in our survey. So we have 323 divided by 1404. So that appears to be, let's see, 323 divided by 1404. That's what I said. All right, so that is pretty much almost exactly right on 0.23. So here, without too much thinking about it, we could go ahead and calculate it via, the hard way. But here, q hat will just do 1.00 minus 0.23, and that gives us 0.77 for q hat. All right. So now, the reason that I was talking about the z subscript alpha over 2, the reason that I got so anxious to address what that was, it's because we need that for the error bound. So another important formula, one that we have to just go ahead and commit to memory here, is that the error, the margin of error, is going to be z subscript alpha over 2 times the square root of p hat times q hat, all divided by n. So a little bit cramped in there to write all of that out. So we'll probably have to take 2 lines to put this here. So we'll say positive 1.65. I guess, if we want to get technical about things, we can leave out the plus or minus, since we're going to bring in the plus or minus when we add and then redo it, but subtract the error, the margin of error. So we can really leave out the plus or minus. That makes it messy, but oh well, we'll live with it. All right, so then we've got the square root of 0.23 in place of p hat times 0.77 in place of q hat, and that's all going to be divided by, so that where did it go? That n is inside the square root, so we have to complete this division and then compute the square root of all of that, and then multiply by 1.65. Or if you want to do it all at once, you certainly can. How would that work? It looks like I would type in 1.65 times, and here the square root will act like parentheses. So as long as we just have included enough parentheses on the inside of the square root so that we're making it do what we hope it's going to do, we'll be okay. So I'm just going to go ahead and include an extra parenthesis. So I'll say parenthesis, we'll do the top, we'll do 0.23 times 0.77 in there. We'll close that off, and then we'll just say that whole thing is divided by, oh, I can't see my keys. That whole thing is divided by 1,404, and then we'll close off that second set of parentheses that was what was all inside the square root. So now we've got all of that stuff inside the square root, and we get out 0.0185, and we'll round it off there. So that's going to be, what did we say? 0.0185. So the general rule of thumb for rounding for proportions is we're going to round to 4 decimal places, regardless of what the original data had as its significant place values. So now finishing up the true proportion, P. Remember, P hat is the sample, P is the true population proportion, is going to be what? P hat plus or minus our margin of error. That's how I write it. Okay, so we'll just go ahead and plug that in. We've got 0.23 plus or minus this margin of error, 0.0185. So on the one end of it, the proportion is in between. Well, let's see, the upper end is 0.2485. And then on the other side of this, we're going to have 0.21, I want to say 0.2115. Let's just double check with the calculator. So we've got 0.23 minus 0.0185. And yes, sure enough, that is 0.2115. So there is our 90% confidence interval for this proportion. What does this mean? Forget what we were talking about, but oh yes, it was the student loans. How did students finance their education? So our sample said 23%. But 90% confidence, right, means we're only going to be wrong 10% of the time, that the true proportion, whatever it may be, is in this range from 21.15% up through 24.85%. All right, so I'm going to sign off here since nobody came to my virtual Q&A. Probably was my fault because I'm still working with Canvas. So signing off until then. Bye.